So this is the 47th session on relative velocity. This is in continuation with the 46th session. Okay. So in this session also we will discuss relative velocity numerical problems of mutually translating frames. Okay. In this video we'll discuss the case 2 of relative velocity problems for mutually translating frame. In order to know what is case 2 of relative velocity for mutually translating frame, you just go back to 42nd video. In the 42nd video, you will get the details of all the different types of relative velocity problems for mutually translating frames. So it is based on that one. So you can go to the 42nd video and see it there. Okay. So in this problem session, we will take up a river man problem. Okay. So we are given a river, we are given a swimmer. Swimmer is crossing the river. We will discuss all types of relative velocity problem for this case. Okay. So first we will make assumption regarding the river. Okay. We make an assumption regarding the river. Okay. So assumption are this. This is the assumption. Of river. Assumptions of river man problem. Okay. Assumptions of river man problem. First of all, river will be denoted by R. River will be denoted by R. Okay. So regarding the river, what will be our assumptions? River is assumed to be a straight river. Straight river. Straight river, okay. And the velocity of river flow with respect to ground is uniform and constant. Uniform meaning what? At any instant of time, all the river particles have the same velocity with respect to ground. And second, constant meaning it doesn't change with respect to time, it is same. So VRG meaning velocity of river with respect to ground, that is equal to U say, that is constant, it doesn't change with time. And at a given instant it is same for all the river particles. All the river particles have the same velocity, that is U. All the river particles have the same velocity, that is U, okay, with respect to ground, and is a straight river. Okay. So in top view, the situation will be something like this. This is the top view of the river. This is one bank, this is the other bank. River flowing at a constant speed U with respect to ground. Okay, and width of the river is assumed to be L. L is the width of the river. Okay. L is the river width. Okay. L is the width of the river. All right. U is the uniform constant flow velocity of river with respect to ground. Okay. This is the one bank, this is the other bank. Okay, fine. Then instead of man we write swimmer. All right. Which should be denoted by S. So velocity of swimmer with respect to river, VSR, that is V say, and which is a constant quantity. Okay, but that is it is independent of time. Okay. Now one more thing, all the river particles have the same velocity U. So river translates with respect to ground. Therefore, for the case of translating frame, VPF equal to VPM plus VMF, we write here as VSG, velocity of swimmer with respect to ground, is equal to velocity of swimmer with respect to river plus velocity of river with respect to ground. VSR is nothing but vector V and VRG is nothing but vector U. Alright. So this is the introduction of this river man problem. Okay. Whatever assumptions are required, they have been stated here. Fine. All right. So now I'll grab it. All right. Now one more thing. How do you define the heading of the swimmer? Heading of swimmer means the direction of vector VSR, velocity of swimmer with respect to river, implies direction of VSR, that is velocity of swimmer with respect to river, VSR. Direction of VSR, that is the velocity of swimmer with respect to river, VSR, that is V. Direction of V, that gives the heading of the swimmer. Alright. So instead of swimmer, if you have a boat, then VBR meaning heading of the boat meaning direction of vector VBR. VBR meaning heading of the boat meaning direction of the vector VBR. Alright. So this means heading. Okay. Now the problem is like this. Suppose a swimmer is initially at a point on south bank of river and swims across the river to a point on the north bank. It is being assumed in this case that the river flows towards east. Okay. The swimmer heads of theta with the river flow velocity. Okay. And VSR is equal to V, VRG is equal to U, as stated just now. Also, VSR equal to V, say, and VRG equal to U, say, constant. Both are constants. U and V are both constants. Okay. So now, first of all, we have been asked to show the swimming process on a diagram. Okay. Show the swimming process on a diagram. This is the first thing. You have to show the swimming process on a diagram. All right. I'll have this. Okay. So I'll show the swimming process on a diagram, alright? So in the top view, I show the swimming process. I show the swimming process in the top view. So VRG is U, rightward, as stated just now. This is the south bank, this is the north bank, this is the river. This is the river, alright? This is the south bank, this is the north bank. Swimmer is the object under consideration. So VSG is equal to VSR plus VRG. That is just equal to vector V plus vector U. This is VSG. Alright. VSG is just equal to vector V plus vector U. Now if we add these two vectors, we get VSG. So we add using the parallelogram law of vector addition. This side we have U, this is VRG. This is VSR, that is V. If we combine these two parallelogram method, diagonal of the common tail through U and V, diagonal of this parallelogram through the common tail of U and V, this is the vector VSG. This is the vector VSR, this is vector VRG. This is the angle theta, alright. So the swimming process will be something like this. The body axis of the swimmer is aligned along VSR. The body axis of the swimmer is aligned along VSR. So it's like this. See, this is the swimmer, okay? This is the head, this is the feet. Now the VSR is always in this direction. VRG is in this direction. VSG is in this direction. So as seen from ground, it is something like this. See, like this. This is the swimming process on diagram in the top view. So swimmer, the body of the swimmer is like this, and as seen by the observer on the ground, the body of the swimmer moves like this, in this way, something like this. If this is the swimmer, this is the feet, this is the head of the swimmer, then the body axis of swimmer is something like this, and it moves like this. See, in top view. I would like to just say that it is not that body of the swimmer moves in this direction as seen from ground. No, the body is aligned like this, and body translates in this way, drifts in this way. Okay, it's not that body goes like this. Body is like this, and as time passes by, body of the swimmer moves like this. See, this is how the body of the swimmer moves. All right. So this is how the body of the swimmer undergoes the motion while crossing the river. All right. Fine. So one thing I have done, alright. Now second thing we have to define what is meant by the drift of the swimmer, and second, what is the time taken by swimmer to cross the river. Define the drift of the swimmer. We denote this drift by D. Say drift is I define in this diagram. See, this is the starting point of the swimmer. This is the point of the swimmer just opposite to the starting point on the north bank. Swimmer starts from here. This is the point on the north bank just opposite to the starting point of the swimmer. And swimmer moves like this, and when he crosses the river, he comes somewhere here. So this distance is called the drift of the swimmer, D. D is called the drift of the swimmer. So how do you define it in words? Distance through which the body of the swimmer moves along the direction of river flow while crossing the river. That is the drift of the swimmer. Alright. So drift will be equal to what? Distance moved by the swimmer along direction of the river flow while crossing the river. That is the drift of the swimmer. Along the direction of river flow while crossing the river. That is the drift of the swimmer. All right. How to define the time taken by swimmer to cross the river? Swimmer is initially here, and after some time when he reaches the river here, he crosses the river. The T is the time taken by the swimmer to move from this point to this point. That is called the time taken by the swimmer to cross the river. So T is the time taken by the swimmer to cross the river T. Alright, fine. Now this I'll rub it, okay? This also I'll rub it, alright? So first we have defined the river. What are the assumptions regarding river? What data are given? River width L, VRG U, VSR V, and all the flow velocities U and V, they are all uniform and constant, okay? Then we showed how the swimming process appears to a person standing on the river ground. How the swimming process appears to a person standing on the ground. The body of the swimmer like this, moves like this. Then we define what is the drift of the swimmer, what is the time taken by swimmer to cross the river. Alright. I'll wrap it, okay? Now we have to find first what is T and second what is D, drift of the swimmer. Okay, these two things we have to find out. All right, I'll rub this to make it slightly clear. Okay. So see, I'll again redraw the diagram. Okay. So this is the top view of river. I'll rub this also. Okay, and this also I'll rub it. Okay. So see, this is the width of the river L. Swimmer starts from here. This will take the origin of the coordinate system. This is eastward direction. E1 hat is a unit vector along eastward direction. E2 hat is a unit vector normal to direction of river flow velocity. We represent the swimmer by point. Okay. The swimmer is here at time 0. Swimmer moves something like this as seen from ground. This is the direction of VSG. This is the direction of VRG. That is U. This is the direction of VRG, that is U. This is the direction of VSR, that is V. This angle is theta. We complete the parallelogram. This is the vector VSG. Swimmer starts from here at time 0. At some arbitrary instant T, the swimmer is somewhere here, S bracket T. S bracket T means swimmer at time T. T plus dt seconds later, swimmer comes here. Here to here, vector is dr, displacement of swimmer with respect to ground in time t to t plus dt. And swimmer finally comes here at time capital T. And this is the start point just opposite to starting point of the swimmer. This distance is equal to d, drift of the swimmer d, while crossing the river. Okay. Now what we have to do, we have to find T and D. Alright. So to find T, There are two methods. Method 1 M1 and method 2 M2. Alright. There are two different methods for finding the value of capital T. Method M1, method M2. Alright. Now how to find T by method 1, method 2? That is the question. Alright. So now see, we'll write on this way. So from here to here, this is the displacement of swimmer with respect to ground in time 0 to small t. From here to here. From here to here, okay? RT. Now VSG dr by dt in ground frame. Alright. In ground frame is equal to VSG, that is equal to VSR plus VRG. Alright. This is nothing but vector V plus vector U. Alright. Then I shift dt right side, is equal to V dt plus U dt. Alright. Then I integrate this equation on both sides. Alright. 0 to capital T, 0 to capital T, and 0 to R bracket T. R bracket T meaning position vector of swimmer at time capital T when it just crosses the river. So this one, integrating it, we get R bracket T minus 0. So now VSR is V, constant. So V comes outside the integral. dt, 0 to capital T. VRG is U, because that is also constant. So this also comes outside the integral. 0 to capital T. Alright. So now I'll rub this. Okay, fine. Now R bracket T is the position vector of swimmer at time capital T, at the instant when it just crosses the river. That is from here to here. Here the straight line vector from here to here is R bracket T. It is nothing but the displacement of swimmer with respect to ground in time 0 to capital T. So now this displacement has two components. A component along this direction which is LE2 and component along river flow which is DE1. So net displacement R bracket T can be written as D into unit vector E1 hat plus L into unit vector E2 hat. That is equal to V. Integral dt 0 to t is t. Integral u dt 0 to t is ut. Alright. Now VSR, V can be broken into two components. Component along E1, component along E2. So I write this as V cos theta E1 hat, V sin theta E2 hat into t plus u. U is just along E1, so vector u will be written as u E1 hat into t. Alright. So now right side E1 I take common. So this becomes V cos theta plus u into capital T plus V sin theta into t into E2 hat. Here E1 hat was missing. Okay. Alright. E1 I take common here. V cos theta plus u into E1 t plus V sin theta into t into E2. Alright. So now we compare these two equations. We equate the coefficients of E1, E2 on both sides, the respective coefficients. So I first equate the coefficient of E2 on both sides. So left side L, right side it is V sin theta t. Alright. So t becomes L by V sin theta. Alright. This is L. Alright, thick. Alright. So from this we get T is equal to L by V sin theta. This is the time taken by the swimmer to cross the river. This we have found by method 1. Alright. Now we find time t by another method. Okay. Now you find t by method 2. See, method 2 is this. The swimmer moves from here to here along the straight path at a constant speed Vsg. The total distance moved by the swimmer is just equal to Vsg into capital T, because Vsg is constant. When speed is constant, the distance covered is speed into time. Since Vsg is constant in magnitude and direction both, the distance moved by swimmer in time 0 to capital T will be Vsg into capital T. Now that total distance moved by swimmer is just this distance. It is the vector sum of these two distances, okay, d and l. So it is that from Pythagoras theorem, it becomes root under l square plus d square. So t becomes this, l square plus d square by Vsg. This is the method 2, okay. So these are the two methods by which t can be evaluated. Alright. Now, one more thing. You would like to know the value of drift. The equation which I just wrote before rubbing it, if we equate the coefficients of E1 on both sides, then left side the coefficient of E1 was how much? D, and right side it was how much? V cos theta plus u into what? T. This is the drift of the swimmer, D. Alright. So this is the drift of the swimmer while crossing the river. D is equal to V cos theta plus u into T. This is the velocity of find the final value of drift. Okay. Now we can say one more thing. V cos theta plus u is what? This is the component of Vsg along direction of E1. See one more thing. See, this is Vsg. Suppose Vsg makes an angle of phi with unit vector E1 hat. Alright. Now we can write Vsg in this way. Vsg is equal to Vsr, that is vector V, plus Vrg, that is vector u. Now we take the dot product of this equation with E1. Vsg dot E1 hat is V dot E1 hat plus U dot E1 hat. Alright. So this becomes Vsg dot E1 hat becomes what? Vsg into 1 into cos phi, that is Vsg cos phi dot product rule. V dot E1. V is in this direction, E1 is this, angle is theta. So this will be V into 1 into cos theta plus U dot E1. U in this direction, E1 also in this direction. U into 1 into cos 0 degree. So Vsg cos phi is V cos theta plus U. This is substitute here. So this drift can be written in one more way. Component of Vsg along direction of river flow, which is denoted by Vsg11 into T, is the drift of the swimmer while crossing the river. Where this quantity, this quantity is just Vsg parallel, that is component of Vsg along the direction of river flow. Alright. So drift also I found out, time also I found out. Alright. This I'll rub it, okay. Now one more thing, this capital T we found in method 1 and method 2. See, by method 1 T is obtained to be how much? V sin theta, alright. So now V sin theta can be interpreted in one more way. What is that? See, this equation I'll write here again. Vsg equal to vector V plus vector U. We take the dot product of this equation with E2. Okay, unit vector E2. So this becomes Vsg dot E2 hat is equal to V dot E2 hat, U dot E2 hat. Now Vsg dot E2 hat is just how much? That is just equal to Vsg into 1 into cos pi by 2 minus pi from geometry which I rubbed just now. That is just cos of pi by 2 minus phi. And what is V dot E2? This becomes magnitude of V, 1, V into magnitude of E2, 1, and into angle between V and E2, that is pi by 2 minus phi. 5 by 2 minus 5, and u dot e2 becomes 0 because u and e2 are mutually perpendicular. Dot product vanishes. So this means VSG sine phi is equal to V sine phi. Okay. So we can interpret V sine phi in two ways. Component of VSR normal to river flow direction. This is V sine phi. VSR perpendicular to river flow direction. Component of VSR perpendicular to river flow direction. That is V sine phi. So we can replace. Sorry, this is with theta. Sorry, this mistake by theta. Just a small calculation mistake. V sine theta. Okay. So V sine theta is nothing but, is it clear? You have just a small calculation mistake. It will be phi theta here, not phi. Okay. So VSG sine phi is same as V sine theta. That is component of VSR perpendicular to river flow direction. That is VSR, V sine theta. So we can write this as, we'll denote this symbol by VSR perpendicular. Okay. So time taken by swimmer to cross the river can be written as L by VSR perpendicular. Okay. Where VSR perpendicular means V sine theta. That is the time taken by swimmer to cross the river. Alright, fine. So we have found the expression for drift. We have found the expression for time taken by swimmer to cross the river. Two formulas. One is L by VSR perpendicular. Another is root under L square plus D square by VSG. Now whichever is known, we substitute in that equation and we get the result. Alright. This I write it, okay. Last point, one more thing I'll say lastly. For T to be minimum, find T minimum. T minimum meaning minimum time taken by swimmer to cross the river, and also corresponding value of theta. So now just now we found T to be how much? L by V sine theta. Alright. Now for T to be minimum, sine theta should be maximum. For T to be minimum, sine theta should be a maximum amount. That is how much? Plus 1. When theta is equal to how much? 90 degree. Alright. So then T minimum will be equal to L by V sine 90 degree. That is just L by V. And when theta is 90 degree. Theta means 90 degree meaning, in order that the swimmer crosses the river in minimum time, heading of the swimmer, that is VSR, should be perpendicular to the river flow direction. So for T to be minimum, the heading of the swimmer should be perpendicular to VRG. Okay. Now how will the swimming process appear in this case? Is the top view of the river. This is the starting point of the swimmer. VSR makes an angle of 90 degree with VRG. VRG in this way, rightward, U. VSR is 90 degree with U. So this is the direction of VSR. This is the direction of VSG. Now the heading of swimmer will appear to be like this. As seen by a person standing on ground, the body of the swimmer will appear to be moved like this. the body will appear to head towards north and the body will drift something like this way. So this is the swimming process of the swimmer for the case when time to cross the river is minimum. Okay, so T minimum, this is the swimming process as seen by a person on the river. And what is the corresponding drift? Just now I wrote drift is what? VSG parallel into T. VSG parallel is what? Component of VSG along river flow direction, which is just the component of VSR along this, which is 0 plus U. 0 plus U into T. 0, T becomes L by how much? V. This is the corresponding drift of the swimmer while crossing the river when the time taken by swimmer to cross the river is minimum. This is the case when time taken by swimmer to cross the river is what? Minimum. In that case, this is the drift of the swimmer. Alright. So this on the 47th video, I have explained all the types of riverman problem and all the various parameters. I have fully introduced it. What are the assumptions and what are the relevant quantities of interest which I have given. Alright. In next session on this relative velocity also, I'll take up some more problems on riverman problem. Okay. So I close it here. Alright. Fine.